West, I'm the Math Club president. I'm also tonight's speaker. Hopefully you're in the right room. This is a meeting of the Math Club. If you're not a member of the Math Club and you would like to join after this talk, or maybe it would be better to join before you get a bad impression, just talk to me or any of the other officers. Victoria, right there, Allison, Kai Hansen, and Cameron, and is there anyone I'm missing? Yeah, I said Allison.
Okay.
Yeah. Anyway, just talk to them if you're interested in learning about Math Club. It's an organization where we host talks like this and social events. So usually I introduce the speaker, but tonight the speaker is myself. So I don't really feel the need to introduce myself except to say that I am a student here at UGA, like almost all of you. I'm a fourth year math and English double major, and this is my first Math Club talk, so I'm very excited, and I want to thank you for coming out. So the subject for today's talk is recipes for pie. And in case you didn't know, this is in honor of Pi Day, which was this Monday. I was just not on top of my game enough to have the talk this Monday. But this talk will be about recipes for pie, and I want to start with one. So, well, this isn't a recipe for pi, this is a question. So if you take the natural numbers and you square them, and you take the reciprocals of those and you add them all up, 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, etc., what do you get? This is called the Basel Problem. And it's not called the Basel Problem because there was a person named Basel. It's actually called the Basel Problem because there's a town named Basel where several mathematicians lived who all were trying to figure out this problem. Among them were Leonhard Euler and also the Bernoulli brothers, all famous mathematicians.
And it's not called basil because you put basil on your pizza?
It's not called, yeah, otherwise it'd be an I. So the Bernoulli brothers worked on this for years, I think decades. And they knew approximately what this was. They knew it was about 1.6994, I think. But they wanted an exact value. They wanted to know, why is it 1.6994? And they spent a lot of time on this, and they never got anywhere on it. Well, they never found a solution anyway. But Euler did. And his solution was very surprising. So Euler in 1734 figured out that this sum is equal to something no one expected. It's equal to pi squared over 6. So there's no obvious reason why this should be true, at least to me. If it is obvious to you, we should talk and write a paper. In fact, this is the opposite of obvious. Pi is the ratio of the circumference of a circle to its diameter. Why should it, much less the square of pi, be involved with the sum of the reciprocals of the squares of the natural numbers? Not obvious, right? And it's not only non-obvious, it's also very beautiful, very aesthetically pleasing. The fact that pi would be just related to the natural numbers in this way is surprising. So tonight's going to be about 3 recipes for pi. And this is going to be the first recipe. So we're going to go through deriving their formulas, recipes, formulas. We're going to be deriving 3 formulas for pi. But we're going to start with this one. And for this one, we're going to follow the same pattern that Euler did in discovering it. In other words, we're going to go through his proof. And it's a really cool proof. But to start off, we need to talk about, so Euler's strategy was to extend something we know about normal finite polynomials to what we call infinite polynomials. So I want to go over this thing that we know about finite polynomials first, and then talk about how we extend it to infinite polynomials. So let p of x be a polynomial of degree n. So it would look something like a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on, adding more and more terms until you got to the constant term a0. And suppose that p of x1, it has in non-zero roots, which we'll label R1 through Rn. So first, suppose it has this. And then second, an additional condition, suppose that p of 0 is equal to 1. So the point of this is that say we know the roots of a polynomial, we can express the polynomial as a product of linear factors where each linear factor is x minus one of the roots. So for example, if we had x squared minus 8x plus 15 or something like that, well, 3 is a root because 3 squared minus 8 times 3 plus 15, that's 9 minus 24 plus 15. So that would be 0. So 3 is a root, and we can also see that 5 is a root. So 25 minus 40, oops, plus 15. So so 3 and 5 are roots, and as you would expect, we can factor this as x minus 3, x minus 5. Just, I mean, like we all know. And in general, if you have roots R1 through Rn, then you could factor p of x as x minus R1 times x minus R2 times x minus R3 and so on all the way to x minus Rn up to some constant factor c. Because the same function, or one function, two functions can share the same roots, but one can be like curvier than another, and that factor of c controls the scaling of the polynomial. Okay, but we have this additional requirement though, that p of 0 be 1. And so that means that 1 is p of 0 is c, and now each of these, if we replace each of the x's with zeros, then we get negative R1, negative R2, and so on, all the way to negative Rn. So that must mean that c is equal to 1 over those things. So just doing a little rearranging for cosmetic reasons, we can rewrite p of x. We can always write a polynomial that satisfies these conditions in this form. X minus R1 over negative R1, x minus R2 over negative R2, and so on, all the way to here. And over negative Rn. Or if you prefer, which for the sake of this talk we will, this format. 1 minus x over each root. So, nothing too profound here. This should be pretty similar. Just should remind you of factoring in the old days when you were a child. So this is the result, hopefully we all understand, for finite polynomials. So Euler's big idea was, Euler said, this should work for infinite polynomials. And so what did he mean by infinite polynomials? Well, infinite polynomials basically means a polynomial that goes on and on and on and never ends. So we've talked about an nth degree polynomial over here. There is no highest degree for an infinite polynomial. It just goes higher and higher and higher. There is no limit to the degree. And so to give you that sounds really weird, but it actually makes sense. And I want to give you an example. We can use infinite polynomials like this one to approximate functions which are interesting to us, like the sine function. And so we end up, and then this goes on where it's just the next odd number after each one. Does everyone know what the factorial symbol means? Okay. So, right, so some of you may remember from a trig class or something that near 0 you can approximate the sine function as the constant function x. But it's not very accurate away from 0. It quickly becomes inaccurate. So if you wanted to include more terms, say you included these two terms, x minus x cubed over 3 factorial. This would be a more accurate, here, let me add a little bit further to my sine function. Then x minus x cubed over 3 factorial would be a somewhat more accurate approximation to the sine function. It's accurate over more of the interval. And then you could keep going. You could say, you could add the 5th degree term. And it would look, I think it would look like this. 1, 2, 3, 4, like this. And so the more and more terms you add, the better and better your polynomial becomes as an approximation of your function. And that principle continues as long as you want. The more terms you add, the better your approximation becomes, until finally, when you don't put any limit on how many terms there is no approximation. It's an exact representation of your function. And so anyway, we call these infinite polynomials Taylor series. For those of you who haven't seen them before, Taylor series play an important role in calculus, and they are the sort of infinite polynomials that Euler had in mind when he was thinking of this idea. So let me find what I did with the eraser. And this is kind of a mess. So this is the Taylor series for the sine of x. But we're going to be interested in a function, the sine of x over x. And so the division with infinite polynomials works much like you'd expect. You just go turn by turn. So we have 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial, etc. And so you may ask, well, why are we looking at the sine of x? The answer is, we're looking at the sine of x because this is the one function where this trick will work. The reason Euler became instantly famous when he solved this problem is because no one else had been able to for decades. And he must, who knows how many functions and how many ideas, thousands of ideas he looked through before he found the one that worked. So we're going straight to the answer. But Euler had to search all over the place. So you may ask, well, how did I think of this? I didn't think of it, Euler did. And it really is amazing. You'll see how it works out. So this is the Taylor series for the sine of x over x. But now we want to apply Euler's idea to it. And Euler's idea is, let's just treat this infinite polynomial like a finite one. And so let's find out what its roots are. First of all, what are the roots of sine of x over x? And then you want to tell me one.
Does 0 count?
No, that's a good point. 0 doesn't count because the function isn't defined at 0. And actually, because you bring it up, I was hoping I could avoid it. But we actually have to define our function a little bit carefully. This function right here makes perfect sense except at 0. It looks kind of like this. But at 0, it's not defined. There's a little hole here. So what we want to do is just fill in the hole by saying that at 0, this function will be 1. So what we'll do is we'll just say that our function, we'll call it f of x, is 1, and I apologize for the spacing here, is 1 when x is 0, and it is sine of x over x when x isn't 0. So what we end up with is a smooth function like this.
I was just hoping you'd put 0 into the whole thing on the right side. And then you get 1 minus a bunch of zeros.
Well, we will be doing that. We will. But first of all, roots. So 0 is not a root. What is a root? Can somebody give me a root?
Pi.
Pi. Okay, pi. Good. Can someone give me another root?
Negative pi.
Thank you. Okay, I need one or two more.
2 pi.
2 pi. Thank you. Okay, and so yes, any multiple integer multiple of pi will do, right? So we could just go plus or minus 3 pi, plus or minus 4 pi, etc. So now we have infinitely many roots. And that's very different from when you have finitely many roots. But Euler's big idea was to say, well, let's just see what happens. Maybe it'll work out. He didn't know it would work out. He was just guessing, maybe this will work. And then we need to satisfy one other condition, which was that p of 0 is equal to 1. And this is where Dr. Clipper's question comes in. This isn't defined at 1, but since we defined this new function that plugs the hole, so to speak, we do have that f of 0 is 1. And so now if we just go from analogy, from the finite case to the infinite case, we should be able to come up with a formula for sine of x over x. So we'll say that sine of x over x is equal to 1 minus, and then x over its first root, which is pi, times 1 minus x over its second root, negative pi, and we'll rewrite that as 1 plus x over pi. And likewise, we have 1 minus x over 2 pi, and 1 plus x over 2 pi, and so on. We have this infinite product going out to infinity. And this is a lot to write, so just so you know, mathematicians usually use this notation for a product. The product from n equals 1 to infinity of, oh, hang on, we need to do a step to simplify, because this wouldn't be that easy to write out as a product. Okay, so the simplifying step is that these are factoring out, these are factoring the difference of squares. So if we multiply these pairs of terms out, we get 1 minus x squared over pi squared for these two. And then for these two, we get 1 minus x squared over 4 pi squared. And then out here, where I ran out of room on the board, there'd be 1 minus x over 3 pi and times 1 plus x over 3 pi. And so when you multiply those together, you get 1 minus x squared over 9 pi squared, and so on. Okay, so now we can write this in a more condensed form using this notation here. And this symbol, this isn't pi. Well, it is pi, but it's capital pi. And capital pi doesn't stand for a number, it stands for multiplying things. Multiply. Just like the sigma symbol means to add. So anyway, we'll be multiplying all the terms of this format all the way from n equals 1 to infinity. And so this was Euler's hypothesis, that sine of x over x is equal to this crazy infinite product. And like I said before, he didn't know that this was right. And it actually took about 100 years before anybody knew he was right. And what I mean is that Euler, he followed this to its conclusion and came into really strong evidence that he probably was right, but nobody was able to prove it until somebody named Weierstrass, who made this theorem called the Weierstrass factorization theorem. And the statement of the theorem was that Euler is innocent. Now, the actual statement of the theorem is a statement in complex analysis that says that you can factor entire functions in this way. But for our purposes, all we need to know is that way later, about 100 years later, Weierstrass came back and said what Euler did was legitimate. So we don't have to worry. But Euler didn't know at this point, and so but you'll soon see how, in a sense, he did. So he had expressed the sine of x over x in two ways. One, oh well, I erased it, but once as a sum, here, and I'll rewrite all this so you can see it. Once as a sum and once as a product. So now we're going to compare the two and see what we can find from that. So let me erase the board some. Does anybody have any questions while I raise the board? All right, so the idea is that comparing these two ways of expressing the same function will allow us to find out something, the theorem that we're interested in, proving that crazy identity for pi is what will come out of comparing these two formulas. So we have 1 minus x squared over 3 factorial plus x to the 4th over 6 factorial minus x to the 6th over,
5.
There we go, 5 over 7 factorial, etc. is equal to this infinite product. 1 minus x over x squared over pi squared. 1 minus x squared over 4 pi squared. 1 minus x squared over 9 pi squared, etc. So it's not obvious how we draw information out of this. But what I want each of you to do in your heads is to expand this infinite series of factors and tell me what you get. Just kidding. So just like you can expand a finite number of factors to get a full polynomial, you can expand infinitely many, actually. Even though it might seem like it doesn't make sense, you actually can. And the way you do it is by starting small. So we'll just think about one part of the polynomial at a time. And so we would think if we multiplied all of this out, what would our constant term be?
1.
1. Why do people say 1? It's because there's no other way to make a constant term except by multiplying 1 times 1 times 1 over and over and over again, right? And yes, it is true that if we multiplied all of this out, the constant term would be 1, which agrees with this, which is good because they should be equal. Okay, now let's talk about the coefficients of 0. That was meant to be a circle indicating where we would put a coefficient. The coefficient of x. What's the coefficient of x? Somebody said something?
0.
Who said 0? Why do you say it's 0?
There's no single x term. I guess x of degree 1 in that.
So there's no way to make x, so x won't have any coefficient. So x is out of luck. Okay, so we're on a roll. So now let's go on to x squared, which I put an ominously long coefficient on. Can somebody give me one way to make x squared? To make an x squared term out of this? So the idea is pick one entry from each monomial and then multiply all those entries together. And so I want you to pick entries so that the product, once you do all those products, ends up being something x squared. So what would be one way to do that?
Times 1/2 times 3.
Um,
Well, it has to equal 3 factorial. Or negative.
Not right away.
Not right away though. So the thing is there may be more than one way to make an x squared. So let's start with one of them. We could choose this term, negative x squared over pi squared, and then we could just choose 1 every time after that, times 1, times 1, times 1, times 1, times 1, and so on. So that would contribute 1x squared. So that would contribute a coefficient of negative 1 over pi squared to our coefficient of x squared. But there's more than one way to make x squared. We could have chosen 1 here, we could choose 1 here, and then we could choose the x squared term here, negative x squared over 4 pi squared. And then we just choose times 1 times 1 times 1 times 1 times 1. And that would contribute another x squared. So this contributes to the coefficient as well. And so hopefully you're starting to see the pattern. We could have chosen 1 here and 1 here, but then chosen the x squared term here, which has the coefficient of negative 1 over 9 pi squared, and then just kept choosing 1 over and over again. And so that would contribute 2, and so on. Now, is there any other way to make an x squared than like this process we've been doing? No. So the reason is because our idea has been to choose exactly 1x squared. If you choose 0x squareds, then you have a constant term, which is not what we're trying to get. If you choose more than 1x squared, then you have a a power of x higher than 2. And we're only interested in x squared. So this must be the coefficient of x squared in the expansion of this polynomial. So, okay, well these two are equal, so that must mean the coefficient of x squared is equal. So, and this is the trick. That must mean that negative 1 over 3 factorial is equal to that coefficient over there, negative pi squared minus 1 over 4 pi squared minus 1 over 9 pi squared, etc. And so now we're really close. So negative 1 over 3 factorial, that's negative 1 over 3 times 2 times 1, so that's negative 1/6. And then on the right-hand side, we've got a common factor of negative 1 over pi squared in all of them, so we can factor that out. 1 plus 1/4 plus 1/9. Oh. Somebody said, oh. So now we just multiply by negative pi squared on both sides, and look what we've got. We've got 1, which is 1 over 1 squared, plus 1/4, which is 1 over 2 squared, plus 1/9, which is 1 over 3 squared, plus 1/16, which is 1 over 4 squared, etc. So this is how Euler did it, which is really incredible to me. Because, you know, it's like we had a map of where the treasure was, and so we went like straight to it by the most direct route. Who knows how long he had to wander around blindfolded, basically, until he figured this out himself. So we're really lucky to be able to not have to figure this out. So anyway, that is the first recipe for pi. Now, does anybody have any questions before we move on to the second one?
Do you know how long you worked on this?
Sorry?
Do you know how long you worked on this one individual problem?
That's a good question. I know the problem was posed, and I think it was posed in the 1600s. And I know he solved it in the 1730s. But that's about all I know. So probably he was aware of it for several years, at least. But no, I don't really know the answer to your question. Any other questions? Okay. So yeah, in summary, I like this one a lot because it relates pi to the natural numbers. It's very elegant, very simple. And the next one we're going to look at is going to relate pi to the odd numbers. So okay, what was it? Let me look up the date. Okay, so now the next one is a recipe by Leibniz. So Leibniz he's famous as the co-inventor of the calculus with Isaac Newton. He also came up with this formula for pi. And I don't actually have the exact date he did it, but I do know he lived between 1646 and 1716. So, you know, somewhere in there. Probably toward the middle. And his was a formula for pi over 4. And this was an infinite sum. Leibniz's was an infinite sum too. He said start with 1 and remove a third. Then put back a fifth before removing a seventh. Then add a ninth and subtract an 11th and so on. So do you see the pattern? So you're alternating between adding and subtracting the reciprocals of the odd numbers. So this related pi to the natural numbers, this relates it to the odd numbers. And this has a very different, each of the three recipes we're going to look at have very different proofs. They're not connected much at all, really. Which is sort of neat. It shows that you can come to pi in different directions. From different areas of math, you can approach the same thing. And that's a common theme in math, how it's interconnected and you can find one subject in another. So anyway, for this one, our strategy will be to evaluate an integral, a definite integral, the integral from 0 to 1 of dx over 1 plus x squared in two ways. Okay, so now someone may ask, or not ask, but I'm going to address the question, why this integral? It's the same question, it's the same answer as y sine of x over x, because it's the only integral that will tell you this. That's the short answer. They didn't derive it, they didn't come to this deductively. They just tried out hundreds and hundreds of, they worked for hundreds and hundreds of hours on mathematical problems until they realized this worked. And so we're going straight to the solution thanks to all the time they spent. So we're going to evaluate this integral two ways, and the first way is with the fundamental theorem of calculus, or the FTC as we call it for short. Now, how many of you have taken a calculus class? Okay, a fair amount of you, but not all of you. For everyone who hasn't, I apologize. But stick with me. So for the fundamental theorem of calculus says that if you have a function f of x, and you're taking indefinite integrals from a to b of its derivative, f prime of x, then we actually know what that will be always. The definite integral of the derivative will be the original function evaluated at the endpoints of the interval you're considering. So it'll be f of b minus f of x. So, brownie points. Who can tell me what f of x we need to choose for this integral? Who?
Well done.
Arc tangent x. Why do you say that?
Because the derivative of arc tangent x is 1 over 1 plus x squared.
That's right. You get an extra piece of pie. So f prime of x, if you didn't know this, or if you did know this and forgot, or if you did know this and suppressed the memory after your calculus class, the derivative of the arctangent of x is 1 over 1 plus x squared. So this is exactly what we want. Now we can express our integral here, the integral from 0 to 1 of 1 plus x squared, dx over 1 plus x squared, in the format that we know works for the fundamental theorem of calculus. So we know that our result will be f of x evaluated from 0 to 1. In other words, it'll be, an f of x is the arctangent function, so it'll be the arctangent of 1 minus the arctangent of 0. Okay, so we'll leave this term for a minute. Does anybody know, first of all, what is the arctangent function?
What
It's
equals?
the inverse tangent. It's the function you apply to undo what the tangent function did. So the arctangent of 0 will give you the angle whose tangent is 0. So what is an angle whose tangent is 0?
Anytime sine 0.
Yeah, and specifically, because of the domain of the arctangent function, it's 0, I think. Yeah, 0 is the arctangent of 0. Now, what angle do we choose to get such that the tangent of that angle is pi 4? Pi over 4, that's right. So for those of you to whom this is a mystery, the reason they're saying this is because on the unit circle, if you look at an angle of pi 4ths, then at this angle, the intersection of that ray with the unit circle is the root 2 over 2 times root 2 over 2. And so the tangent of pi 4ths is defined to be the ratio of the sine of pi 4ths over the cosine of pi 4ths. But this is the special point at which they're equal, and so the ratio is 1. So that's right, pi 4ths is the answer. So we found that this integral equals pi 4ths. So that was one way. So now and notice pi 4ths corresponds to the left-hand side of this equation. So now we're going to evaluate it another way and get the right-hand side. And because we're evaluating the same integral two ways, our two results must be the same. So that's our strategy. Right. So the second way we're going to do it was with the power series, the infinite polynomials we talked about earlier. So we said, so we're going to try to make a power series for 1 over 1 plus x squared. And to do this, I'm going to refer to a fact that I hope that some of you might know. If you don't, it's okay. Recall that the sum 1 plus r, so r is a real number, 1 plus r squared plus r cubed plus and so on. So adding up higher and higher powers of r converges to the number 1 over 1 minus r when the magnitude of r is strictly less than 1. And just as an aside, it converges only when the magnitude of r is strictly less than 1. Because if r were 1 or bigger, then you'd be adding 1 plus 1 plus 1, and that would go away to infinity. But if r is less than 1, then these powers get smaller and smaller and smaller, and so the sum makes sense. So to do a quick example, we would have 1 plus 1/2 plus 1/4 plus 1/8, and so on. That would add up to 1 over 1 minus 1/2, which is 1 over 1/2, which is 2. And this makes sense because if you're running a 2-mile race, you run the first half and you've run 1 mile. And now you have a mile remaining and you run half of that. So you run another half mile. And now you have a half mile remaining, you run half of that, so you run 1/4 of a mile. And then you run half of the remainder and you run 1/8 of a mile. And 1/16, and so on. And so this is a sort of intuitive way of seeing how this infinite sum adds up to 2. That's just one case, but hopefully for those of you who haven't seen this before, it'll be enough to convince you that I'm not pulling the wool over your eyes. So now that we have all this, we're going to use that fact for this, and we'll just say set r equal to negative x squared. Then 1 plus, okay, r would be negative x squared, plus r squared would be plus x to the 4th, plus r cubed would be minus x to the 6th, plus r to the 4th would be x to the 8th, etc. And so this is true when the magnitude of negative x squared is strictly less than 1, right? And that holds if and only if the magnitude of x is less than 1. So now we've got this way of expressing our integrand here as an infinite sum. So what I want to do is I want to replace 1 over 1 plus x squared with the infinite sum. So let's see. 1 minus x squared plus x to the 4th minus x to the 6th, plus and so on. Is there any problem with this? There is a problem, because I asked. Does anybody know what the problem is with this? What? What about the upper bound?
It's 1.
Why is that the problem?
It'd be strictly less than 1.
Right, exactly. So good. We said that this substitution works only when x is strictly less than 1. But we're looking at this function on the interval from 0 to 1 inclusive. And this works on the interval from 0 to 1 exclusive. So what we've done is technically illegal. So fine, you caught me. I'll just change things a little bit and we'll just get through a loophole around that problem. So the integral we're interested in is this still. But now I'll just say, well, okay, well this is equal to the limit as t approaches 1 from the left of the definite integral from 0 to t of 1 over 1 plus x squared dx. So now this integral lives strictly on 0, t, and t is strictly less than 1, so it's valid. So it's valid to make this substitution. So I found a loophole around the laws of math. And that's all I need to get as far as I need to go. Because now that this substitution is valid, we can just do standard calculus procedures to evaluate the integral. So we're taking the limit of an integral. Let's just evaluate that integral. We just do antiderivatives. So the antiderivative of 1 would be x, of x squared would be x cubed over 3, and so on. And now this should start to look suspiciously familiar. 7, and so on. And we're evaluating that from 0 to t. Now, when we evaluate at 0, we'll just get 0. 0, 0, 0, 0, 0. So 0 does nothing for us. All that we have left is the t. So we have the limit of t minus t cubed over 3 plus t to the 5th over 5, etc. But this is a continuous function. An infinite polynomial is continuous. And so that means that to evaluate this limit, we can just plug in 1 wherever t is. And so we conclude that our limit is, our integral rather, is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus dot dot dot. And now, of course, this is what we were headed toward. This is what we wanted, because we also showed that that same integral is equal to pi fourths. And so here we have another way of expressing pi, this time as in terms of the odd numbers. So this is 2 recipes for pi, and I want to pause because if you want to make pi at home, you need to have the right ingredients. So does anybody have any questions before I go on? Okay. Thank you for humoring the bad jokes. So the third and final recipe we're going to be talking about is my favorite of the 3. I didn't know about it until I started doing research for this talk, whereas I knew, and maybe some of you knew as well, about the first one we did with the pi squared over 6. That one's pretty famous. The one we're going to look at next isn't really famous, but I think as famous, but it deserves to be because I think it's really more impressive than either of the other 2. But I'll let you be the judge. So this one was also discovered by Euler in 1737, so 3 years after his other one. And this one's a formula for pi eighths. And I'm going to start writing it out. This time it's an infinite product. Have we seen an infinite? Yeah, we saw. Did we see it? Have we seen an infinite product yet? Okay. So this one will be an infinite product. Look for the pattern as I write out each term. So it starts with 2 over 4 times 3 over 4 times 5 over 4 times 7 over 4 times 11 over 12 times 13 over 12 times 17 over 16. Okay, do you want me to add one more term? Or does anybody want to make a guess as to what the pattern is? All right, I'll add one more term. Times 19 over 20. And then it keeps going. So can anyone tell me what the pattern is? Well, let's start with the pattern on the top. What's the pattern in the numerators?
Prime numbers.
It's the prime numbers. 2, 3, 5, 7, 11, 13, 17, 19 are the prime numbers. So now what's going on in the denominators? We've got 4, 4, 4, 4, 12, 12, 16, 20. Can anyone, is there any rhyme or reason in that? Anybody want to hazard a guess? Jackson?
I just said Roman numbers, but I have no idea.
No, all that's, well, not as far as I know. It's actually pretty simple. All that's going on is we're in the denominator, underneath a given prime, we're writing the multiple of 4 that's closest to that prime number. So 20 is the multiple of 4 closest to 19, 16 is the multiple of 4 closest to 17, and so on. The sort of special case is 2, which is equal distance between 0, technically a multiple of 4, and 4. But since we can't divide by 0, we divide by 4 here. Yeah?
Is 8 closer to 7 than 4?
I'm sorry. I probably made this a lot harder to understand. Okay, now does this make sense? Sorry, my bad. Okay. So, this one is the last one, so if you're ready to get out of here, that's the good news. The bad news is it takes longest. And so if you do need to go, feel free to step out at any time, but I'm hoping to get this done in a reasonable amount of time. The reason this takes long is sort of as you might expect, as this is kind of the weirdest recipe we've looked at today, this will take the most interesting and most complicated methods to prove it. And so to start on our way to that, and I want to give one more teaser. You remember we just did that pi over 4 is 1 minus 1/3 plus a fifth minus a seventh and all that. This formula here will be derived from that one. So we're going to be deriving an infinite product from an infinite sum, which is really mind-blowing. I did not even know this was possible, like I said, until I started researching this. So to do that, we're going to be using something called an Euler product. But before we get there, we need to introduce a few prior ideas that are built into the definition of an Euler product. So let me give you a few definitions. So first, definition. Right. Let S be a complex number and A of n a function of the natural numbers. So then we call a series of this form, a series of the form, it goes from n equals 1 to infinity of A of n divided by n raised to the s power. We call this a Dirichlet series. Dirichlet was another mathematician a little while after Euler, or maybe at the same time. I actually don't know. But anyway, he was a mathematician who was also studying these things. So this is called a Dirichlet series. And let's introduce one more definition. A function f is called totally multiplicative. If f of a b is equal to f of a times f of b for all a and b, and one more condition, f of what was the condition? Right. F of 1 equals 1. So we add this last condition just so that we can't have f equals 0. Because technically, if we didn't have this condition, then 0, just the constant 0 function, would be a totally multiplicative function. And that would throw some things off. So we add this one condition at the end to get rid of that possibility. So basically, a totally multiplicative function is one that respects multiplication. So can anybody think of an example of one?
Constant function 1.
Okay, good. So a constant function, f of x equals c, that respects multiplication because it doesn't even include the input at all.
Only if c is 1 or c is 0, but you rule out 1. So yeah, it has to be f of x is 1.
Oh yeah, you're right, actually. My bad. Can anyone think of a non-constant function? Dr. Clipper is making a big X. What?
X squared.
Okay, x squared. X cubed would work too, right? Because whenever you have, in general, when you have any polynomial, x to the n, when you take ab to the n, then the exponent distributes and you have a to the n times b to the n, which is the same as f of a times f of b. So yeah, those are the things, sort of things we're talking about when we talk about a totally multiplicative function. But the one that we'll be interested in, which we'll get to in a little bit, is not nearly so, it's pretty weird. So you'll see. Right, so the next thing, okay, so we have all the definitions in place that we need for us to talk about the Euler product, which is the thing I brought up earlier. And this is what's going to allow us to make the transition that I described from an infinite series, which I've erased, to that infinite product. So the Euler product. And this is one of the biggest theorems in number theory, especially analytic number theory. And you'll see why, well, at least once we talk about it some, because it's really cool. So let A of n be totally multiplicative. Then the Dirichlet series sum of, A evaluated at n over n to the s. Oh, s is a complex number like it was before. And we're letting n run from 1 to infinity. Then this Dirichlet series is equal to the infinite product. Here's that symbol for product again. 1 over 1 minus a, your function evaluated at p times t to the negative s, where p is a prime number. So in other words, like p is 2, 3, 5, 7, 11, and all those things. So this is not like our normal sums or products where the numbers range from 1 to 10 or something like that. This is a special one that ranges over the prime numbers specifically. And so this is a pretty deep theorem, which I'm not prepared to prove in its totality, but I want us to look at a small example that will let you get the idea of why this is true. Because actually, it's really amazing. Okay, so the proof, we're going to do a really simplified case. The simple case where, okay, well, our totally multiplicative function is 1, and s is equal to, what did we decide? S can be whatever we want, but just for the sake of our mental health, let's assume s is a real number, since we don't want to think about exponentiating something by a complex number, unless you've taken complex analysis. So s is a real number. Okay. Then we can take this product down here. And so then the claim would be that this product of 1 minus 1 minus 1 over, 1 over 1 minus, okay, a of p is always going to be 1, and then p to the negative s. That this product, ranging over all the prime numbers, is going to be equal to the sum 1 over n raised to the s, where n ranges from 1 to infinity. So this is the claim. So it should be obvious now how to prove it. Just kidding. But it will actually become clear momentarily. So we're going to start on the left-hand side and work over to the right-hand side. Would it help you guys if we would it help you all if we substituted s with like a real number like 2 or something? Would that make it any clearer? I see at least one person shaking their head, so it won't actually change anything at all. For those of you who prefer the generality, you can just replace the 2 with an s. But hopefully this will make it a little bit more concrete. So this infinite sum, by the way, is the one that we said earlier was equal to pi squared over 6. That's not actually relevant, but just to spur your memory. So let's expand this sum. The prime numbers start with 2, so we start with 1 over 1 minus 2, the negative 2 times 1 over 1 minus, okay, 3 is the next one, and then 5, and so on. And then we keep going. Now, the trick we're going to do is that, do you remember how we said 1 over 1 minus r? Here, let me do this in a space. We said how 1 over 1 minus r is 1 plus r squared plus r cubed and all that. Well, that applies here. Now our r's are prime numbers raised to the negative 2 power. So we can actually think of each of these terms as an infinite sum. And that may seem like a step backwards because now we'll be taking a product of infinitely many infinite sums. But I promise it'll work out, so just trust me for a little bit. So it'll be, let's see, 1 plus 2 to the negative 2 plus 2 to the negative 4, and so on, times 1 plus 3 to the negative 2 plus 3 to the negative 4, and so on, plus 1 plus 5 to the negative 2 plus 5 to the negative 4, and so on, and so on again. Okay? So, remember how a while ago with the pi squared over 6 one we expanded an infinite product? How we took that infinitely many linear terms and expanded it into a polynomial? We're going to do that now with this. And so, can we make the number 1 out of, so I want us to pick one entry from each parentheses, and then with the understanding that we'll multiply together each choice. So is there any way to make 1 out of our choices?
Yes.
Yes, because we can just pick 1 every time, right? 1, 1, 1, 1, 1, and so on. So our sum will be 1, or I'll write it 1 over 1 squared. Now, is there a way to make 1 over 2 squared? What should I do?
Pick the 2 to the negative.
Okay, so I'll pick this one, and then I pick 1, 1, 1, and so on. Now, is there any other way to make 1 over 2 squared? There's not, right? Because this is the only, because we move on to higher prime factors later on. We're never going to get back to another 2. So, okay, what about 1 over 3 squared?
Yes.
Same idea, right? You just pick a 1 here, and then you pick a 3, this term here, and then you pick 1, 1, 1, so you get a 3 squared. Now what about 1 over 4 squared? This one will be a little bit different.
There's
Yeah, just pick the 2 to the negative 4.
Yeah, that's the only difference. I didn't mean to imply anything profound. Now we just pick this term, and 1, 1, 1, and so on. And now notice how we're able to find every number, and we find it only once, so far, right? And this will keep going. And the reason it keeps going is because each real number can be uniquely factored as a product of primes. So that's what we learned in 3rd grade, that you can take a number and make a factor tree and figure out all its prime factors, and that's the factorization. There's only one way to do it. And this function generates every combination, so it has to generate every number. So that's why we got 1 over 1 squared once, and 1 over 2 squared once, and 1 over 3 squared once, and 1 over 4 squared. And we will continue to get that all the way through all of the natural numbers, because each natural number is uniquely related to one of these choices. And so that means that that's our proof, right? That's what we wanted to prove, that this is the sum of 1 over n squared from n equals 1 to infinity. So basically, Euler's product formula comes down to the fact that we can that every number can be factored uniquely as a product of primes. So I don't know about you, but I think that's really cool. And more to the point, if you're here for the pi, this will quickly lead to a formula for pi. So let me erase the board. Does anybody have any questions about this proof? I know I'm going a bit fast. You're a very quiet audience. So we're going to use the, I won't erase this because no one but me will remember it. Now we're going to use the Euler product formula to get this formula. And remember that I said I promised you that we would be able to get it from this sum here. Pi 4 equals 1 minus the 3rd plus the 5th minus the 7th, etc. Now, oh shoot. Well, I just erased the definition, but is this a Dirichlet series? Does anybody remember what a Dirichlet series was? Hopefully some of you do.
N to the x.
Does this count as a Dirichlet series?
Doesn't look.
Somebody, you're shaking your head, no, why?
Because it's not, the denominator is not raised to a complex number.
So the denominator, well, first of all, we're missing a bunch of denominators. We're missing 2 and 4 and 6 and 8. We're missing all the even denominators. So that's one vote no. Does anyone vote yes?
Those can be written as being raised, 3 can be written as being raised to a complex number.
Well, here our complex number is 1, because the real numbers are the subset of the complex numbers. So it's not a matter of powers, that's all right. We're just raising everything to the 1. So that's okay. Jackson?
Yes.
Okay, but what about what he just said?
So there's nothing against the ANs being zeros, is there?
No.
So like all.
So what if we rewrote this 1 over 1 plus 0 over 2 plus negative 1 over 3 plus 0 over 4 plus 1 over 5 plus 0 over 6 plus negative 1 over 7. Now is it a Dirichlet series?
Yes.
You're still skeptical.
Yeah.
So it is a Dirichlet series because we have a function. It's a simple function. It just alternates 1, 0, negative 1, 0 over and over again. But it is a function, and we have on the bottom each natural number raised to a complex number, namely 1, which is a very boring complex number, but it's the one we're interested in. So this is a Dirichlet series. We just need to write it in this format. I'll call this chi of n over n. We need to define this function here that goes 1, 0, negative 1, 0. And if we can define this, so if we can define this function and we can show it's multiplicative, then we can apply Euler's product, and then we can just go to town with it. But the only thing we need to do is supply this function and prove it's multiplicative. So how would we define this? What's the pattern is 1, 0, negative 1, 0. But when is it 1? When is it 0? Well, if you look at it, when the number is of the form 4k, then the function is 0. So,
2k.
Well, yes, 2k. Yes, 2k. So when the number is even, the function is 0. Okay, well what if when the number is equal to 4k plus 1, so in other words, when the remainder of the number after division by 4 is 1, then our chi is 1 as well. I need to put numbers here, 0, 1. And then negative 1, when n is of the form 4k plus 3. In other words, when the remainder after division by 4 is 3. So for instance, 3, the remainder after you divide 3 by 4 is 3. So this is negative 1. 7, the remainder after division by 4 is 3. So this is negative 1. So this is our function. And this is a perfectly valid function. And so now I'm going to make the claim without proving it that chi is indeed multiplicative. Not you, Kai, but it is indeed multiplicative. I've worked it out. It would fill up a lot of room and be boring. You can just trust me on it. It is multiplicative. So that means we can apply Euler's product to get that this infinite sum is equal to an infinite product of 1 over 1 minus. Okay, now our function is chi of p, the prime numbers, times p to the negative 1, because 1 is the number we chose. And again, p ranges over the prime numbers. So if we just rewrite this a little bit, we get the product over the primes. Let's multiply on both sides by p over p. So p over p minus c of p. All right, well, let's expand this. So the first prime is 2, so that would be 2 over 2 minus, what is chi of 2?
0.
0, so 2 minus 0. And then the next prime is 3, so 3 over 3 minus, what's chi of 3?
1. What?
-1, okay. Then times 5 over 5 minus, what's chi of 5?
1.
Minus 1, okay. Times 7 over 7 minus what's chi of 7?
-1.
-1. And so you see what's happening is chi is taking each prime to the nearest multiple of 4. Just like we wanted it to. So our result is, well, 2 over 2 is 1, then 3 over 4 times 5 over 4, that's good, and 7 over 8, which I did wrong before, but now it's right, and so on. And so, right, so we have this, but this sum here we had shown was equal to pi fourths. So this is equal to pi fourths. If we just multiply by 2/4 on each side, this would be pi eighths is equal to 2 over 4. And that's what we were trying to prove this whole time. So we went from a sum, which was pretty interesting in itself, to this crazy infinite series. Anyway, that's all the recipes. Well, I actually have more, but I don't have time to show you. But my point in having this talk was just to show you how amazing some of these formulas are. Nothing you would ever expect. And how we prove them with different areas of math each time. We used ideas from complex analysis, from calculus, from number theory, and it just shows you how interconnected math is, and how part of the beauty of math is the connections between the different subjects. So yeah, as I mentioned, I actually had a lot more material that I cut out for this talk. If you want to know any more formulas for pi, you can just talk to me afterward, and I'd be happy to show them to you and even prove them if you want. And some of them are pretty neat. Unfortunately, I just had to cut it down to these 3 for time's sake. So anyway, thanks so much for coming.
Thank you.